Hey, all right, the third constant acceleration equation. So far we know that if an object is moving with constant acceleration, its motion can be described by these two equations right here. But we can come up with a third one, not by adding anything new to the scenario, but just by eliminating time between these two equations. We know they both involve time right here, and we don't always have information about time in our problems. So it would be nice if we had an equation that related some of these other variables like acceleration and velocities and positions, and equations that related those things without involving time at all. So that's our goal here. Can we eliminate time between these two equations to get a new one, a third one? I'm going to start by writing down equation number 2 here. And first thing I'm going to do to it is multiply the whole thing through by the acceleration, a. So I'm going to multiply the left-hand side by a, and I'll multiply all the terms on the right-hand side by a. So this will be a times a. That gives us a squared on that term. Okay, left-hand side stays as a delta x. But on the right-hand side, I notice something. I've got a times delta t right here. And a times delta t is just equal to delta v. I'm going to use this first equation here to replace a times delta t with delta v. So this term becomes v naught times delta v. I just used the first equation to eliminate time from this term. I'm also going to use the first equation to eliminate time from this term. So a squared times delta t squared, well, that's like a times delta t squared. A squared times delta t squared is just delta v squared. So if I square this whole side, it's equal to squaring this whole side. So this term here is equal to plus a half, that stays, times delta v squared. Again, I eliminated time by using the first equation. All right, next up, I'm going to multiply through by 2. I don't like this 1/2 right here, so I'm going to multiply the whole thing by 2. 2 times that side, 2 times that term, and then 2 over 2 becomes 1 right there. And in the next step, I'm going to examine this delta v, and I'm going to expand that out to be written as v final minus v initial. Okay, so left-hand side is 2a delta x, right-hand side is 2v naught, and delta v, that's v final minus v initial. I'm just going to use the letter v for v final and v naught for v initial. Plus, and then this is delta v squared. So the square is around this whole thing. So delta v inside is v minus v naught, and then the whole thing is squared. I use my parentheses very carefully here to indicate them squaring the whole thing. Next step is to multiply out some of these terms on the right-hand side. So left-hand side doesn't change. On the right-hand side, I'll have 2v naught times v minus 2v naught times v naught, or 2v naught squared. Plus, and I got to multiply out this whole thing, which we know is going to be v squared minus 2v v naught plus v naught squared. All right, it looks like it's getting uglier, but it's about to get better. It gets hairier before it gets, it gets worse before it gets better. Okay, we're about to have some cancellations here. Notice this term, 2v naught times v, and this term right here, negative 2v naught times v. They're going to cancel each other out. Those disappear. Notice this term, minus 2 v naught squared. Here's a like term, v naught squared. So negative 2 v naught squareds plus 1 v naught squared gives us negative 1 v naught squared. This term stays, so I've got v squared and then just minus v naught squared. And that's my whole the whole right-hand side of the equation simplifies down to that. I'll put my left-hand side back in. And this equation is usually written with these two sides flipped. So let me flip them, and then we will have our third equation for constant acceleration. V final squared minus v initial squared equals 2 times the acceleration times the displacement. There we go. One other way to rewrite this, because this is a final thing squared minus an initial thing squared, or it's a final thing minus an initial thing, we can call the right-hand side delta, and then in parentheses, v squared. It's the change in the v squareds. Here's the final v squared, here's the initial v squared. So change in the v squareds equals 2 times a times delta x. Our third equation. Notice that the time has disappeared from here. I eliminated time. So now we can solve situations that only involve displacement, acceleration, and the velocities. Even if we know nothing about time, we can go to this equation. All right, a key point here, mathematics point. Do not make this mistake. If I write in parentheses delta v and I square that whole thing, it's not the same thing as the delta of v squared inside parentheses here. Delta v is v final minus v initial, and if I write with the parentheses like this, I've got to square that whole thing. And this term squared out gives us this. On the other hand, delta v squared means I need to change in what's ever inside the parentheses. So I need final value of this thing minus the initial value of this thing, which is that. This is obviously not equal to this. Therefore, we know that this is not equal to this. Be careful with your notation.